Uh, Good afternoon for all. My name is Edwin Escobar. I'm going to present the San Carlos Dam and the application of hydrostatics in its operation. First one, presentation of the case study. The Puchina Dam and the San Carlos hydroelectric plant owned by Isagen from the hydroelectric complex with the largest installed capacity in Colombia. That is that approx 1,240 megawatts in 8 Pelton units. Commercial operation starts in stage in 1984 and 1987. The dam is in an airfield structure on the Guatapé River that creates the Puchinas reservoir and sends water to an underground powerhouse. Geographic context and site characteristics. The project is in San Carlos, about 150 kilometers east of Medellin, in a mountainous area with heavy rainfall and fast response watersheds. The dam is 70 meters high and 800 meters long. The reservoir has a surface area of about 3.4 square kilometers and a total capacity of 61 between 72 million cubic meters. And the free spillway was designed to pass a probable maximum flood of around 7,200 cubic meters per second. Hydrostatics in construction, operation, and maintenance. Hydrostatic pressures increase with depth, creating thrust on the upstream phase and uplift on the base. The hydraulic gradient controls seepage and piping in air dams. Its design and construction. The cores, the filters, and drain limits seepage and reduce pore pressures, and the diversion tunnel works as a bottom outlet with gates. In operation, intake towers and pen stocks carry water to Pelton turbines, each holding approximately 32.7 cubic meters per second. Power is stepped up to uh, 230 kilovolts. Reservoir levels and manage to keep freeboard and coordinate a spillway use during floods. In maintenance, things monitoring segments and seepage, like piezometers and drain flow. Inspect the spillway gates and slopes, control sediment, and keep the SCADA system modernizing. And technical risks uh, out of the San Carlos is not a failure case. Typical risks in air dams include reservoir over elevation from extreme rain, seepage and piping due to high gradients, and uplift if drains fail, and sedimentation that reduce useful storage and changes hydrostatics. The spillway capacity and the bottom only are the key mitigation barriers. Effects and consequences. Uh, Environmental effects include change to riparian ecosystems, variations in downstream flows, and progressive, progressive silting. Management plans at monitoring revegetation and education. Socially and historical, San Carlos faced displacement and conflict impacts in 1990s to 2000s. Reports links territorial tensions and energy projects with shifts in the conflict. Hydropower development was on the factor within broader socioeconomic chains. Economically, and for energy, the 1200 140 megawatts contribution supports national supply and the stability of a interconnected system. Finally, lessons learned and reflections. Designing spillways with safety margins lowers the risk of overpressure and overtopping at the seepage controls. Kids guidance within safe limits, adaptive reservoir management during rainy seasons, protects the structure and rear bands. Predictive maintenance based on piezometers in kilometer and dry flow readings enables early actions, including social participation, remediation, and territorial development helps reduce the conflict and increase the local benefits. This is all. Thanks for your attention.